The main goal of this study is to propose a new methods to characterize multi-scale and heterogeneous composite materials of complex shape. This is a very important topic in the field of thermal characterization. Here we try to develop a new methodology based on flying spot technique associated with automatic KUKA robot to be able to characterize such composites. This experimental setup is associated with image and inverse processing method based on analytical solution and image reconstruction.
The device we have developed is based on a laser beam to make the thermal excitation of the sample and an infrared camera to record the answer. We have to work on small regions of interest to have enough spatial resolution. So to work on large and complex shape, we have first of all to draw the part with computer-aided design and transfer this file to the KUKA robot in order to move region of interest after region of interest to make a complete scan of the 3D shape. We will work on this complex 3D shape. So we have to draw with computer-aided design. First time in 2D. When it's okay, I will put the part in 3D, as you can clearly see here, with the right dimension. And finally, we obtain this 3D part.
We arrive and we can fix the sample on the robot.
So we can use two methods to program the robot arm position. The first one needs to place the sample at the focal plane of the camera. So we can move the robot manually. This is very time consuming, and the second way is to use the 3D models that we have already done, and we can export this model in a STL format toward the KUKA, and there is an automatic programming, an offline programming of the different positions of interest. So each position can be moved automatically with the KUKA robot. As you can clearly see, we're always in the same focal plane, and the laser beam will be always normal to the sample surface.
Here you can see the laser diode, which is wavelength of 900 nanometers and which is collimated by a lens here. This light will go inside the galvanometric mirror. Here we have a f-theta lens, which allow to bring the beam on this dichroic mirror. This dichroic mirror is treated to reflect the visible wavelength of the laser, and then you arrive here on the sample. And when you warm up the sample, the infrared emission passes through the dichroic mirror, which is semi-transparent to the infrared and is measured by the camera. We adjust the focus of the infrared camera.
Okay, so now for each region of interest, we have to move the laser beam with the galvanometric mirror. We will have 49 positions on 7 lines and 7 columns. So we use a LabVIEW program to move the galvanometric mirror, and we use an infrared camera to record the answer of the sample to this thermal excitation.
At the end of the experimentation, we are going to analyze the data. For that, we have a homemade software which allows us to first upload the data we have measured, so we can check the data. So here we have the measurement of one region of interest. When we have that, we need to subtract the baseline. So we are going to subtract the average images, so we obtain this system, And then to make the logarithmic parabolic method, we need to label the spot. So here we have a possibility to make a threshold of the system. So we can choose the area of interest of each spot. And then when we have done that, we can go to calculate and visualize the properties, and we obtain at the end the thermal diffusivity field. So we can also check for each spot that we obtain a parabolic method as well as the linear step. So we can see here that everything was nice. We can check the spot we want. We obtain the result of the measurement. When we have extract all the data from the region of interest, we need to check the order here. We have done the scan like this, and in the angle here we have cut in two images, and we will keep only the measurement made on this. And with that we can reconstruct the complete experimentation, which was made like this. So we can see each of 52 region of interest, and here it's like if we have done the experimentation at the same moment. So we can see the bigger image. Here we obtain 700 by 1000 data, and from this image we can reconstruct the complete thermal properties along x and y direction of the sample. Here we obtain the complete map along x direction, the y one in y direction, and then we can apply this into the true shape of the sample here to analyze here the properties along x and also along y. This is along x and y direction.
So this device is devoted to non-destructive testing, and it allows to explore or to inspect real size pieces as industrial materials or for industrial applications. In this case, in this experiment, we try to fix the optical parts, the camera and the laser, in order to analyze the samples. But for other applications, more complex or more real, we are able to embed all these parts into the robot to be able to attain big surfaces or difficult geometries. And this might give us the opportunity to inspect many materials or many complex systems as airplanes or oil and gas plants or plastic parts which have very, very difficult geometries and which are difficult to explore usually. What I might say is also that this is a very versatile technique that can be applied into other fields that we have not explored yet.